Welcome to Science and Engineering World, where we use the principles of mathematics and science to think engineering, act engineering, and practice engineering. In this presentation on fluid mechanics, I will be discussing one important property of fluid, which is density. My name is Olutola Fakehinde. In a previous video I made on fluid, I will put the link at the top and in the comment section below. I made mention that one of the characteristics of fluid is that it does not have definite shape of its own. It takes the shape of the container it occupies. I will go further on that because if you put a liquid inside a container, depending on the quantity of the liquid, it will take as much of the shape of that container. However, if you put a gas in a container, it will occupy all the space that is given to it. Even if you give more space, a gas will continue to occupy all the space. Density is a significant property of any substance, and it is very important to fluid mechanics. So we're going to look at it into details. And there is a symbol, a Greek letter rho, that we normally use to represent it. And what is density? Density is defined as the mass of the substance per unit volume at standard temperature and pressure. Mass per unit volume. That is, if you take 1 meter cube of a container and you fill it with the matter of the substance and you weigh that, whatever we get divided by the volume will give us the density. And this standard temperature and pressure is temperature at 0 degrees Celsius and pressure at 1 atmosphere, which is sometimes approximately 1 bar. Mathematically, we can now define mass density as mass density symbol rho is equal to the mass of the substance m, representing m, and the volume of the container. With capital V for volume. Just with the symbol alone, we can then say that rho equals to mass over volume. Now, what is the unit of rho? The unit of mass is kilogram, and the unit of volume is meter cube. So we can now say that rho, that's density, equals to mass over volume in kilogram per meter cube. So this is the definition for density, mass density, and let's give it a number, because it's one of the significant values we need in mechanical principles. So we just denote it with a letter 1, because we'll be using this as we go on. The second one is weight density, which some people refer to as specific weight. And we have a Greek letter gamma to denote it. So what is weight density? The weight density or specific weight is the weight of the substance per unit volume at standard temperature and pressure. The weight of the substance, weight per unit volume at standard temperature and pressure. Now we need to make a distinction here. Mass and weight are not the same thing. Mass is not the same thing as weight, because some people always interchange this. They are not interchangeable. Mass is the matter that a substance is made up, and this is always the unit of it, because it has a unit of kilogram, which we have seen above. And weight is a force. It's a force either exerted on the matter or exerted by the matter. So it is a force. Weight is a force which has a unit of mass times acceleration. Mathematically, we can now write weight density which we say has a symbol gamma, is equal to the weight of the substance, which is mg over volume, unit volume. V. So we can now write, so with the symbol alone, we can then write gamma equals to mg over V, which we can also write as m over V times G. Now if we recall from that equation 1 above that I say is very important, we have seen that rho, that's density, equals to mass over V. So in this case, if we bring that into this expression, so we can now say that mass over V here is now that density. So we can write our weight density as gamma equal to rho times G, and this is, it has a unit because mg like I said, which is the weight, is a force. And the unit of force is Newton, which is Newton, and then per volume, which is meter cube. So specific weight is rho g, which has a unit of Newton per meter cube. So let's call this one expression 2. The third one we want to look at is specific volume. It has a symbol nu, which is another Greek word, nu, or some people use small v for it. Specific volume is defined as the volume over mass, the volume per unit mass. So in this case, we're talking about a substance which weighs 1 unit mass, and what is the volume that it occupies. Mathematically, we write specific volume which can use a small v for, is equal to the volume, that's the total volume, capital V, over the mass. With just the symbol alone, we now write small v equals to capital V over m. But from the expression 1, we know that density, or mass density, rho, is equal to mass over volume. Now, if we look at these two, we see that this is the inverse of the density. So we can write specific volume, small v, to be equal to 1 over rho. Or write this as rho to the power of minus 1. So our specific volume is now equal to rho to the power minus 1. We know the unit of the density to be kilogram per meter cube. So the unit of specific volume will now be meter cube per kilogram. And so this is kilogram. And this is the specific volume. With this as a unit. So let's call this expression 3. The fourth one is specific gravity. Specific gravity is defined as the specific weight of a fluid to the specific weight of a standard fluid. That is specific weight of a fluid to the specific weight of a standard fluid. Specific weight of a standard fluid. So what do we mean by standard fluid? If the fluid is liquid, the standard fluid is taken as water. If the fluid is gas, the standard fluid is taken as air. So we can now see from that definition, the definition says that is the specific weight of a fluid to the specific weight of a standard fluid. In this case, we are looking at specific weight of other fluids other than water and air. So let's look at the mathematical definition of this. So mathematically, we can write specific gravity S to be equal to specific weight of a fluid over the specific weight of a standard fluid. So we have explained what the standard fluid is all about. Now let's write it in the notations. From our second definition, we can now write specific gravity S is equal to specific gravity, that's specific weight of a fluid. We have used gamma to represent specific weight. So specific weight of a fluid over specific weight of a standard fluid. Specific weight of a fluid over the specific weight of a standard fluid. Specific gravity of liquid is equal to specific gravity of a liquid over specific gravity of water. Same thing will be when we are writing the gas. So it's going to be specific gravity of gas will be equal to the specific weight of the gas over the specific weight of air. We have seen again from the second definition that gamma equals to rho g. Okay, so let's put this inside our definition for specific gravity. We can now write that specific gravity of liquid, specific gravity of liquid will be equal to the density of the liquid times G over the density of water times G. Good. Now, because we have gravity on both sides, so the gravity will cancel out for both the numerator and the denominator, and we now have specific gravity of liquid to be equal to density of liquid over density of water. Because it is density over density, then it has no unit. It's a dimensionless number. Before we round up, I would like us to look at a situation where we have two fluids that cannot mix in a container. So if you have this situation, we always see that there is always a line of demarcation between the two fluids which cannot mix together because they have different densities. So this line of demarcation is always called meniscus. However, meniscus is another phenomenon caused by capillary effects, and we will look at this in another presentation. So when we have two fluids of different densities in a container, we see that line of demarcation which is occurring at this place, where we see a liquid at the bottom, and then a gas at the top. So when this takes place, we see that the fluid with a lower density is always on top of the fluid with the higher density. Water has a density of 1000 kg per meter cube, and air has a density of 1.204 kg per meter cube. So let me leave you with the question and answer this. Put the answer in the comment section below. Can air float on water? In summary, you will see that density appears all in the definitions we have had above: the mass density, the weight density, the specific volume, and the specific gravity. And these are important properties in fluid mechanics. If you really find this very useful, give it a like by thumb up. Share with others so that they can enjoy all the benefits we have been enjoying. Then make comments. I would like to see your comments. If you need any more explanation or whatever questions or query, please leave it in the comment section below, and then subscribe. I encourage every one of us to please subscribe to this channel so that this channel can go into different parts of the world. And lastly, think, act, and practice engineering. Until the next time we meet, keep studying.